Hello, are you guys there?
Yes, sir. Assalamu alaikum.
Walaikum
Yes, sir.
assalam.
Assalamu alaikum, sir.
Uh,
Welcome back.
Thank you. Sorry, there were many issues, online classes, and many other things. So that meeting actually went longer than I expected. I thought maybe 10 to 15 minutes, but it took around these 40-50 minutes. Irfan, Abdullah, Bisharul, Kainat, Khalid, Manisha, Nimra. Uh, Ghafoor is not there. Noreen is not there. Who else is missing?
So Gafur will join now.
Okay, Ghafoor will join, and Khalid is not there. Mm.
Sir, I am here, sir.
Khalid is there. Khalid. Saif
Saif is
Saif is missing. Ghafoor has already joined. Okay, so we can start now. I think. Okay, enough. I think enough people have already joined, so we can start. I mean, uh, as usual, today's contents are also very much exciting. Now, we will not only discuss about the concept of embedding, but we will also be discussing about these 21st century concepts like attention, transformer, BERT. These are uh, pretty exciting times in uh, in natural language processing. So we'll see how all these things are working. So I'm going to share my screen and then we can start it formally. Word embedding. So I think we have already been using word embedding for many days in our classes. We know the basic concept. The word embedding means to. Who would like to answer? Raise your hand. What is word embedding? What is word embedding? Just raise your hand.
How how
Okay.
to raise hand, sir? By
Okay.
video?
No. Yeah, raise hand by using this Zoom option.
Okay, right.
Irfan has already raised hand. Irfan, yes, you can explain what is word embedding.
I think word embedding is assigning a suitable words to a particular word, of a corpus. We trained word embedding models on large corpus of text, and they give us numberings. What are the good numbers which can represent this word? Say suppose a word is hello.
And
What will the
how
optimal
we
number?
use that number? Where those numbers go then?
We actually feed these numbers to our neural networks, and we for text classification task.
Okay. Okay. Bisharal, what do you think? You raised hand and then you.
Yes, it's a feature learning technique, as Irfan said.
Okay. And Ghafoor, what's your opinion?
I think embedding is a representation of the text. In first previous approach, like one encode, there was a problem of dimensionality and spots. So this technique solve these problems. Now we have less dimensions, and our text are not spots. And there is another advantage is similarity between the text. Some words like beautiful, nice, these types of words.
Hmm. Right. So I think all of you were right. The exact, understanding of word embedding is, I mean, when you've got text, you cannot directly inject text into neural network. You need to convert it into numbers, right? And then you know that neural network can accept numbers. We have got these neurons, and neurons can have value from 0 to 1. Neurons cannot have value A, B, C, D. Huh? So because text cannot be directly accepted by neural network, we need to convert it into numbers. And when you convert it into numbers, the first thing that came in, it was one hot encoding. If you remember, we have already covered one hot encoding. Uh, I mean, we have seen it many times. For example, word embedding or word converted into numbers. If I convert it into one hot encoding word embedding, then first I need to see my dictionary. So here, word is a unique word. Embedding or word is already there, converted into numbers. Right now, you can see here in one hot encoded this 0000001. What do you think, Kainat? What this number might be representing? This 0000001. Are you there, Kainat? Are you there, Kainat? What this number is representing? 0000001. What's your opinion? Manisha, are you there? Manisha,
Sir, I think,
Yes, sir.
sir, majority, uh, uh,
Yes, sir,
I think we
I'm
need
here.
to
Manisha,
send a message in group that class has started.
Manisha is there. Manisha can explain it. Irfan, you can write on WhatsApp group that
Sure.
we have resumed. Manisha, go ahead. Explain what this number might be representing to.
So this number representing a word that's contained in a dictionary.
Which number? Which word?
So
Hmm?
the first word in
Not first word.
embedding are converted into numbers.
Not first word. Uh, what do you think, Basharul? What do you think?
Numbers, sir. The word
Numbers.
numbers.
Numbers. Very good. Very good. I mean, see here, Manisha. When we have this dictionary, 1, 2, 3, 4, 5, 6, it means that each word will be of size 6. When it will be of size 6,
Numbers.
yeah, for the first word, the one hot encoded would be 1 0 0 0 0 0. For embedding, it will be 0 1 0 0 0 0 0, and you go on, and finally when you see this numbers is actually the last word. It means this representation is the representation for this word, the word numbers, right? Similarly, this is the representation of, this is the representation of Irfan. This the other one is the representation of Irfan.
Sorry, sir.
What
Sir,
this
embedding.
embedding?
It's for
Yes, this is representing. This is representing embedding, right? Okay, so I mean, when you have got one hot encoding, we say, wow, it's good thing. It can convert your text into numbers, but the problem is dimension. I mean, usually when you've got a data set, it may have maybe 100,000 unique words. Now, if you have got 100,000 unique words, you cannot represent each word by 100,000 numbers. Obviously, it's not a very wise decision. I mean, they call it very sparse, representation, where each word is being represented by the number of words, a number of numbers, which is equal to a number of words in the dictionary. So obviously, it requires data memory and it is quite sparse. So they actually come up with alternate ideas, and some of them are frequency based and others are prediction based. We'll see, both of these. The frequency based are actually three: count vector, term frequency, inverse document frequency, co-occurrence matrix, right? These are the three which are actually frequency based. They will usually consider a frequency of word inside the document. Let's start with count vector. How count vector works, see here. Suppose a corpus C of D document, D1, D2, D3 up to DD. I mean, we have got D documents with n unique tokens extracted out of corpus C, right? So we have got D documents and we have got n unique tokens. Then we'll create a matrix of D by n, where D is number of document and n is unique tokens in all those D document. For example, if D1, the document 1 is he is a lazy boy and she is also lazy, and D2 is John is a lazy person, then what will be the dictionary of this corpus? You can see here the dictionary of this corpus is, we have got he, we have got is, we have got we have got lazy, we have got boy, and then we have got she, huh? is already there, so we'll not consider. And then also then lazy is already there, right? John is a new word, is already there, is already there, then lazy is already there, and then person. You know, these are the unique words in this corpus. You can see here, he is, I mean, you can also remove this stop word. Stop words are those which are really not contributing in the classification accuracy, because when you classify, you are looking for the features which are unique among the documents. So if we have got a document in which there is in each of the document, then it might not be a very good representative. So usually we remove these stop words which are not contributing in classification. So from here we have he, lazy, boy, she, John, person, right? So there are 2 documents and 6 unique words. I'm not considering is and the reason being they are stop word. By the stop word I mean these are the words which are not very supportive in implementing classification. So we usually remove these words before classification. Right. So in this case, for the count vector, we are going to create a matrix, and in that matrix, we have number of rows, which is equal to number of documents, and the number of column is equal to number of unique words. In this case, these are the unique words. Now you can see here in D1, he appears 1, lazy appears twice, because that's true. Huh? In D1, lazy here, and then another lazy. So that is the reason why we say we keep 2 as a value in this cell. Then for boy 1, for she 1, for John 1, and for person 1. Now you can see column is representing a vector. Huh? He, the value for he is 1, 0. The lazy for value for lazy is 2 and 1. Value for boy is 1 and 0. So you can see here this vector, wherever it is appearing, this column is giving us information. Similarly, row gives the information about the document. Row gives the information about the document. So we can use this vector to, send it to the neural network. If you have got bigger corpus, say for example, you've got 8 documents and you've got, say for example, 8 terms, then you can see your matrix will look like this. Then, you can use this as a vector. Right, you can rescale it. You can rescale it to 0 to 1, but you can use this, vector to be sent to your neural network. Because the good thing is, if this term is representing hello, then this can be its, number representation. And when we have got this number representation, it can be, sent to the neural network. Yes, you can rescale it, because we know that we cannot directly send 10 to a neural network. We can send it, but we have seen that when values are not in the range of 0 to 1, they usually damage our learning process, because some of the vectors, some of the variables, some of the features might be shadowing other features. Those features who are having values in thousands, they permanently may hide those features who have got values in tens. So obviously we want to consider all features equal. That is the reason why we usually rescale them at the range of 0 to 1. But nevertheless, I mean, whatever post processing you are doing, but the good thing is this count vector is giving me a word vector, and that word vector is nothing, just its occurrence in different documents. It can be, row first or column first, whichever arrangement is easier for the network, we can do it. We just need to transpose it, and we can have the different representations, right? So this is one way. The second way is term frequency and inverse document frequency. Remember, all these embedding techniques, they come from 90s and 2000s. We need to still understand them, because we need to understand how we reached where we have reached. I mean, today we are talking about BERT, about fast text, about GILO, but we need to understand that what has been our journey. So initially we were actually working on these frequency based word embedding, and count vector was very popular in early 2000. Then another technique is term frequency inverse document frequency. I mean, fantastic. This idea is super. I mean, see here. Term frequency have got two, important formula, two important values. One is term frequency, which is nothing. It is actually number of time term t appears in a document divided by number of total terms in that document. So number of time term t appears in a document divided by number of terms in the document. So here, if I see what is the term frequency for this, so you can see here the numerator will be 1 because the value for number of time and term t, if t is this, then it appears once in this document, right? Once in this document divided by number of terms in the document. So the number of terms in the document is 1, 2, 4 and 8. So term frequency for this equal to 1 divided by 8, right? Now, if you see, what is time frequency for this and what is time frequency for this in document 2? So time frequency in document 2 is actually 1 over 1 over 5. The time frequency of this in document 2 is 1 over 5. So you can see here 1 over 8 is the time frequency of this inside TF, inside document 1, and this value is 1 over 5 inside document 2. Right. Now, what is the IDF? The IDF is actually, log of n divided by n, the capital N divided by n. This n is actually number of document, and this n is number of document a term t has appeared in. It is very important. I mean, if you just rely on term frequency, if you only rely on term frequency, what do you think? If you have got 100 documents, what do you think? What words will be frequent? Raise hand. If you only rely on term frequency, what do you think? What documents will be, what words will be frequent? I want Nimrod to answer this question.
Sir, messy. Word messy.
Not in this document. I'm talking.
Document 1.
No, not in these two documents. What I'm saying, if you've got
Sorry.
if you have got 100 documents,
Okay.
what do you think? What words will be frequent?
100 of document, it depend on the documents now, means what will be the terms
But
in
if it
that
is
document.
if all the documents are from English language, then which words do you think that they will be frequent?
So mostly the stop words like is, am, are, because they are mostly used in all documents.
Exactly. Now,
Yes.
my next question is, do you think these words are good to separate politics document from entertainment document?
Not at all.
Not at all, huh? So what words are
Yeah.
good to separate politics from entertainment document?
So maybe some other words like politics related word like corruption, etc., and sports related word terms. So
Okay. It means that we want to downgrade the importance of those words which are appearing everywhere. I mean, if you have got
yeah.
100 documents, we know that these frequent words which are appearing everywhere, they are not important. We just want to downgrade their importance, right? So that is the reason why we'll use inverse document frequency. Inverse document frequency says if a word is occurring in all documents, then that word is not good word to perform classification. Here, what do you think? Which word is not good for classification?
Is
Irfan, go ahead.
this
Sir,
is
this is and about also.
Very good. I mean, these three words are not good. These three words really are not good to separate document 1 from document 2. If you want to separate document 1 from document 2, you must focus on Messi and you must focus on TF-IDF, right? So these are the two words which we believe are important. We need a formula which can give us quantification which actually shows the phenomena that these words are not important, this word is important. So you can see here, when we saw term frequency of this, it is 1 over 8 in document 1 and 1 over 5 in document 2. Now, when you see its IDF, IDF says n is number of document where it is appearing, and small n is number of document that term t has appeared in, right? So this is actually true, the number of total document. So in our case, you know, total number of documents are, how many documents are there? 2, right?
2.
Now, if you want to see IDF of is, then in how many documents it is appearing?
2.
2, sir.
2, right? So 2 divided by 2 equal to 1. And when you see log of 1, that is 0. That is 0. It
Oh.
means that now if I see TF-IDF of this, it is equal to 0. Wow, we want this, eh? We want to downgrade, you know, the importance of those words which are appearing everywhere. Now, if you see, you know, TF of Messi, TF of Messi, what is TF of Messi? It is 4 by the TF of
1.
Messi is 4 by,
By 1, sir.
1.
no, that's okay. What is TF? Term frequency. Term frequency of Messi. What is term
4 by 8,
frequency
I
of,
think.
what is term frequency of Messi? Nimra?
4 by 8.
4 by
4
8.
by 8, sir.
4 by 8.
4 by 8.
0.5.
4 by 8. Now, if you
The
see,
4 by 8, yeah.
okay, 4 by 8 is its term frequency, right? 4 by 8 is the term frequency of Messi, right? 4 by 8. And what is its IDF? Its IDF is actually, you know, the number of documents total, which is true, and number of documents in which it is appearing.
Messi is appearing.
Is appearing only in one document.
1.
It is true. And if you see log of 2 is 0.30. So overall TF-IDF for Messi is 0.15 because
Yes.
you know, this is log of n by n and this is its TF. So it is 0.15. But the good thing is this becomes 0. Right. So those words which are good for classification, they will have high positive value, and those words which are not good for classification, they will have you know, value approaching to 0. Like in this case we saw the value for a. So now we say that word Messi should be represented by 0.15 and word this should be represented by 0, right? Now obviously when you send these to the neural network and if you add a couple of layers and if you start your prediction, then obviously even DF-IDF type of embedding, they can give you a very good accuracy on those documents which are really separable. I mean, if you really have documents which can be separated from each other, then you know, important words can easily be extracted by using this simple you know, DF-IDF approach, right? Then the third type of frequency-based word embedding. See, all of you, wherever you have question, just raise your hand. When you raise your hand, I will see it. When you will raise your hand, I will see it here. Irfan, you can ask the question.
Yes, sir. Because you know, most of the time we remove these stop words before, you know, for before feature representation. So then what is the need of this TF-IDF approach? Because we already removed these you know, unuseful text
Very good
like
question.
is this.
Very good question. But you know, Irfan, even when you remove a stop word, you will still have words which are not a stop word, but they are not good separator. For example, if I see a document in which I want to classify them as per politics or entertainment, Right. Now, in politics, you know that word is M, R, all these words are appearing, and you know that they are stop word, right? You can remove them from politics document as well as from entertainment document, right? But even if you remove these words, there are still words which are not stop word, but they are not good separator. For example, if you say Pakistan, now, Pakistan is not a good word to separate politics and entertainment because we have, say, for example, uh, Mavish Haya, she belongs to Pakistan. Pakistan can be discussed in entertainment, and Nawaz Sharif also belongs to Pakistan. So Pakistan can also occur into politics document. It means that
Mhm.
those words which are not a stop word, but still they are very common throughout the corpus. When I say corpus, I mean multiple document belonging to different categories. Now, if they are
Right.
belonging to different categories, and these words which are actually not good separator among all these class labels, then you should downgrade them, their weight should be reduced. But the words which are very specific to entertainment and words which are very specific to politics, sports, those should be given high value. For example, the frequency of bat is extremely high when you talk about cricket, but
Right.
frequency of bat is very low when you talk about politics. Right? Yeah, I mean, it's unfortunate that Imran Khan have got bat as a sign for his election, but that's okay. I mean, even then, the occurrence of bat will be quite high in cricket document than in politics document. I mean, they will again and again they will be talking about batting, 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 batting. So you can understand how frequent batting would be. It means in that case, for sports document, this term will be very high for bat, right? And this term will be very, uh, very low. This term will also be very high. It will not be approaching to zero because it will not be appearing in all document. Because it will not be appearing in all document, which means that this TF-IDF, even after removal of a stop word, it can still recognize those words which are not good separator. But those words which are good separator, they will have high positive value. Right. And Nimra, your
Right.
question?
Sir,
Yes.
you told us the reason, okay, the length of vector is the main concern. So
Hmm.
that's why we develop another technique, right? But
Hmm.
I think in these scenarios where we are just counting the frequency, the number means the vector length is again same now, because here here we are again considering the unique words, and we were considering the same unique words in the one hot decoding. So what's the benefit of this
See,
approach?
again, fantastic question. See, Nimra,
So is
if
it
I'm using one hot encoding, then one word will have representation like this, like this, right? Maybe 1,000, bits. Say, for example, this might be just one word. This might be just one word, right? But now, when you have TF-IDF, the one word is just this 0.15. Right. Now, if you want to give multiple words at a time, I mean, when you are in natural language processing, you do not want to give just one word. You want to give multiple words at a time because you do not want to send word alone because you know that word is known by its company. So you say, I really do not want to give one word. I want to give two words. So if you have got 1,000 unique words, so this is representation for one word. And if you want to give two words, you need another, same size vector. And we say, oh my God, this is very expensive. But here, this is just one neuron which is representing this value. If you want to send another word, okay, another neuron. This is another word. So now we are sending two words at a time. We need only two neurons. But in one hot encoding, obviously, uh, memory consumption will be very high. It will be very high dimensional, and we call it sparse. But in dense representation of text, we follow these type of numbering. We follow representation of the words based on their importance. I mean, it is not only that these are dense, but it is also that the more the importance of the word, higher will be its quantified value. Here, I mean, one is here or one is here, both of them are same. I mean, we cannot say this is more important than this one. But if we have got this TF-IDF and this TF-IDF and this TF-IDF, we know that this number has some meaning. This word must be a good separator between the documents, and this word is extremely worst word to separate the document. So there are multiple advantages of using this dense word embedding. The one is they are just one number, and second is that number also carries some meaning. That number means the importance of that word. Right. I hope I have answered your question, Nimra.
Yes, sir.
Okay. Thank you. Thank you.
So I have one question.
Yeah, go ahead. Go ahead. Go ahead, Vishal.
So which is relevant to machine learning actually. So in machine learning, we say feature representation techniques like TF-IDF, count factorizer, hashing factorizer, all of these things. So in mostly to get the informative and non-informative features, we use feature selection techniques like chi-square, ANOVA, FLU, and there are so and so forth. So my question is, I have seen that these feature selection is not employed in deep learning because feature engineering is not a matter in deep learning. Feature engineering is a matter in machine learning. So why is it that people are not employing chi-square? Maybe if they are going to employ it, they're going to select some best features. So it's going to give some good accuracy, right?
Right, 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 right. I mean, I think the question that you have asked is very frequently asked question in deep learning. They say that because in deep learning, we have got this beautiful, backpropagation learning process. You give nothing. I mean, you just give, for example, if you're talking about image processing, you just give original image. You you give original image, the image intensities. You don't need to give color histogram. You don't need to give age histogram. I mean, when you are in machine learning, you will probably engineer feature for yourself. You will take image and then take image histogram for color, image histogram for ages, multiple other features, and you are an expert and you know that these ages matter, you know that color matter, so you actually engineer feature by yourself, and then you give those to some machine learning algorithm. But when you're talking about deep learning says just give me image, I will decide myself what to do with that. That thing, why deep learning is able to do it, because it has got its own learning process. It has got its own, initially it will randomly assign weights, but then when it learns, it quickly understands what is important and what is not important. I mean, we don't need experts to tell us that what is the color of apple, what is the color of banana. We just give images of apple and banana to our neural network. Neural network will itself, by learning process, it will understand how to differentiate between banana and apple. And that is because it has got its own learning mechanism. And believe me, end of the day, uh, neural network is also in a way learning what is color of apple, learning what is color of banana, and it learns by updating weights. It learns by updating weights, because if apple is red and banana is yellow, then the update in weight will take a trajectory which will eventually be separating yellow from red. Now, if apple is circle and if banana is straight, then eventually, learning process, it will be learning ages of, we have got filter which learn ages. They will actually end of the day be doing same thing that we do as programmer, we do as expert. But here in deep learning, we just give original data and let the network learn what are the good features. I mean, you have seen in CNN that we give nothing. We just give digital image and nothing. In audio, you will see that we will just give sequence, we'll just give, the digital audio and nothing. In video, you will see that will give nothing, just path of the video. Everything else will be learned by the network itself. In text again, we are doing nothing. We are just giving the text. Everything else is being learned by the deep learning model. So that is the beauty of this deep learning, because it has the learning capability, and that is because of back propagation. It starts with random bits, but then slowly, gradually, I mean, only two things. Here is input, this should be output. If this is not output, you are wrong, you are on error, update your weights. So you have back propagation, you are updating weight. Is error reducing? No, 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 error is not reducing. It means you have done changes in the wrong direction. Change your direction. So when you change your direction, you see less error, comebacks, you do this back propagation 30, 40 times. Eventually you will see that your network will be able to recognize how banana looks like and how apple looks like. So the thing is, this learning feature network has taken on its own, because it has got its learning ability, how to update the weights. Whereas for SVM, for naive Bayes, for logistic regression, these are very non-SMOD algorithm. They say, give us feature, we will only plot it on some scale and draw the line. That's all. We don't know how to learn feature. You give us feature, we will only draw the it may be line or maybe curve, whatever, but we will tell you what is the based curve which can separate positive from negative. But we need features. We do not understand audio, we do not understand image. Give us color histogram, give us age histogram, and then we will decide where the line should be drawn. That is the reason why, I mean, this is one of the advantage of deep learning over traditional machine learning, that we now don't need to learn features manually, right? Okay, so we have seen frequency based, count vector, and time frequency and inverse Jackman frequency. Now let us see another one, which is co-occurrence matrix. Now see, I mean, as we grew older
Yeah, I add something in it.
in deep learning, do we have any question?
Sir, may I, yeah,
Yeah.
add something.
Yes.
Sir, as Vishal asked that we can give the features
Mhm.
to the neural network in order to improve the accuracy. So we will not be improving the accuracy, rather than we will be decreasing the accuracy, because feature engineering, we may make some mistakes in that. So if we make any mistake in that, that will be result the negative impact over the overall results in our the results. So deep learning model, let it learn by itself. It will learn by itself by looking at the data, and then give the output result as the what is you have, what data you have given to the what world you have shown to the neural network.
Exactly.
I
Exactly.
mean,
Exactly.
sir, but sir, this is not the case always. It depends on problem to problem and data. I mean, sometimes as a human are the best discriminator of the text or the data, and sometimes we let it on machine to learn itself.
Uh,
So we cannot just say this is always true.
Yeah.
We have seen this, and in some tasks, especially when you have a smaller data, right? We as a human can learn understand it better rather than a machine or a neural network. In case of smaller data, it's still machine learning approaches are very effective on those smaller data. But when you have a huge data, very sparse data, then we obviously human has some limitations, so we can let it on a machine. So it depends on the problem and the data.
See, I mean, it is again a subjective discussion. Uh, Abdullah is right in a way that if you engineer features yourself, these the correctness or the accuracy of those features will depend on your expertise. I mean, if you decide that zero crossing and spectral flux are good in audio classification, They may not be the best. There might be some other, features in the audio which might beat zero crossing and spectral flux. But you, as an
Right.
expert, you decided that zero crossing and spectral flux are good features, so you selected only those two features, right? But on the other hand, if say for example you just gave the original audio and let the network decide what is a good feature, then obviously in first case the accuracy will be limited by your expertise. If you are a good expert, you might beat the understanding or learning of deep learning. But if you have made a mistake, that mistake now will be part of the network. So it's a kind of subjective discussion. You whatever you give to neural network will make sense of it. It may be original image or it may be the value for the features. Whatever you give it, based on that, it will make some sense of that data. Neural network is blind. I mean, it does not know that they are giving me a digital image or they are giving me some features which are extracted from the digital image. But
I mean, sir,
generally speaking, when you are in deep learning, come on, do not do this laborious task manually. Let the network do all this dirty work and you will see the accuracy. Network will tell you if I can still learn more. Network will tell you if I'm overfitting. Network will tell you if I need more capacity. So you just need all these basic concepts clear. Then any problem, let the network do the majority of that laborious work rather than you are taking it on your own responsibility.
it's a
So
long discussion in the article, sir, which I shared 3 days back. Is discussing the same thing. After all, the university is you're doing some stats behind and maths behind to learn some useful patterns or so still there are some areas where we as a human are still especially for natural language processing understanding of natural languages, we still feel that these are not enough sufficient to learn those patterns from the data and
Mhm.
explicit useful information.
I mean, as I told you earlier, if you are expert, you might be giving it features which are very good discriminator, right? So what I told you, the learning of the network is limited by your expertise. If you are not a
Right.
good expert, if you have missed something, then network will also miss because you have not given it original audio, original video, or original text. You have given it, the features that you have chosen. So now the ability of network is limited by your ability. So we need to kind of make sense of this thing that feature engineering is one good area that in machine learning was job of the human, but here network has taken it on its own shoulder. And as I told you earlier, it is subjective discussion. And application to
Right.
application, there must be some scenario where you will say you don't need to give whole audio, you just extract these three features from audio, you should be able to get good accuracy. I mean, if you know it, obviously it will then reduce a lot of workload on network. Then you might not need a lot of processing on the audio because you know that these three features are good to, for example, I know that if you've got 5 minutes of silent and 5 minutes noise or 5 minutes music, I know that zero crossing and RMS means signal energy. Now, when you've
Right.
got RMS as a signal energy, you know that if there is a 5 minutes silent, then energy level will be very low. And when there is music, energy level will be very high. So you as an expert are absolutely sure that energy level in silent 5 minute audio will be low and in music 5 minute audio will be high. In that case, it's quite obvious you can extract features and send those features to the network. You are then kind of sharing load of the network. You are now not giving lot of data to the network. You're not giving original audio clip which might be very heavy. Rather you are giving it only small features which are very good separator from silent and music, and you as the expert know that this is a good feature. And when you have done it in machine learning, it gave you 99% accuracy. So there is no reason, if you have this problem to solve and your expertise tell you that energy is a good separator, then do not give audio, give the feature, right? Because ultimately neural network needs numbers. Those numbers
Right.
might be digital audio, might be digital image, or might be features of those digital audio or digital image, right?
Right.
Irfan, go ahead. Okay, I think you are okay now. So we can move
Yes, sir.
ahead. A lot of contents are there. We are already running behind schedule. The next big thing that we came up in word embedding was this co-occurrence matrix. And in co-occurrence matrix, again, I mean, when we were using, TF-IDF, we were just focusing on one word. But then co-occurrence said, well, you should give numbers to words, and those numbers should also have relationship. Those numbers should also be showing you the relationship between two words. For example, if you say good, then it might have value 0.1. And if you say bad, it should have value 0.99, right? Because these numbers are quite opposite from each other. So one should make sense from this embedding. We should say that those words which are similar, for example, when you talk about politics, in politics, you know that the word like dharna and the word like 18th Amendment, you know that both of these words are very similar to each other. They occur very frequently together. Then they should be given numbers which are close to each other. And the numbers which are very opposite to each other, as I've given you earlier the example of a ball. Now we say that ball is word which is very frequently occurring in sports, but not in politics. So we say that these numbers should have different embedding. These numbers should also tell you how different these words are from each other. So those words which occur together, they should be close to each other. And those words which hardly occur together, they should have, very dissimilar values, right? So for that reason, they came up with the co-occurrence matrix concept. For a given corpus, the co-occurrence of a pair of word W1 and W2 is the number of time they have appeared together in a context window, right? And now when you say co-occurrence, you also need to see that how long you can consider, and that is actually the context window. When you see here, and in co-occurrence matrix, here, if I say my window size is true and my word is fox, then window size true means on left, quick and brown, on right, jump and over, right? Similarly, if you say my word is over, then its context window, the word is jump and word is fox. Here the word is there and the word is lazy, right? If you create, suppose a corpus, he is not lazy and he is intelligent and he is smart, right? If the context window size is true, what do you think? What I should write here? The co-occurrence between he and lazy. Just think for maybe 30 seconds and raise your hand. What do you think? What should be the number here inside this column? You will have to see the window of lazy. The window of lazy is here. He is not appearing. And if you see to this side, he is appearing once. Now, if you see another he, it appears here. In its context, we do not have word he, and to this side also we do not have word. We are considering lazy. So lazy, here no appearing of he, and here there is one appearance of he. Do we have another lazy? No, we do not have another lazy. So what should be here? Lazy and he. What should be in this context window? Khalid?
0.
Lazy and he.
Sir,
What should we write here?
Sir, maybe 0.5, maybe.
Come on, it has to be a number. It has to be a number. For example, if you see this one, over.
Yeah.
Now, co-occurrence of over and jump in this case is 1 because jump appears once in the context window of over. And context window, I mean, you give a number, you say context window of 2. Then you see number of words on its, 2 number of words on its left and 2 number of words on its right. So if I say what is the co-occurrence of over and jump, it has to be 1. Now in this corpus, he is not lazy, he is intelligent, he is smart. My question is, what should I write here?
1. 1, sir.
Obviously 1.
After lazy, there is one time he.
Okay, okay. How about is? How about is?
Also, again 1,
Three.
sir.
Sir, 3.
3, sir. 3.
3 or 1?
Maybe
Sir,
2, sir.
3.
Because
Sir, 3.
maybe 2.
3, sir, 3.
Nimra, why you say
Sir, over or you are asking before occurrence or after occurrence?
you know, window means both, left or right.
Sir,
And
3, 3.
Sir, 2.
3.
3, sir, it's 3.
He is. 3 times.
are you sure?
But you guys are not considering the post occurrence. The first time there is he is not. And the again he is intelligent, he is smart. So maybe it's
1, sir.
So what should be the number, Visharal?
In between 1 to 3.
3, sir,
Maybe.
it's 3.
I mean,
most appropriate answer.
here is the word is. It's here. It's the context window is not and lazy. He and there's no other word than left. Right? So 1, right? 1.
Yes, sir. 1.
The next occurrence
I
of
think 1.
he is here. In this context window, yes, he is here. So now it becomes true. On this side, intelligent and he. So this is third occurrence. Now when you come here, here is fourth occurrence. So here I should write 4. Does it make sense to you?
Yes,
No
sir.
clear.
No, sir.
How-
No,
See
No,
here.
sir.
See here.
Sir, this
See
is the
here.
same. We
The
are just
context
counting its
window.
frequency.
The context window of is, you know, is we have here. So, you know, when a window size is 2, so this whole, you know, it comes into the context window. When it comes into context window, I am going to use, कौन सा होता है? ये तो पूरा fill कर रहा है. Okay. Here, पहला, this is the first occurrence, eh? So we have seen he is there. Okay, this is one. And when we consider this one, इसका context window क्या है? 2 इस तरफ, I mean 2 on this side and 2 on this side. It means that for this occurrence, this is the context window. This is the context window. How many occurrences
Yes.
of he are there? How many occurrences? We have
2.
seen 1
Yes, sir.
and 2 more here, so that becomes 3.
Yeah.
3.
Right.
Yes, sir.
Now this is another occurrence of is, and the context window here, 2 on right, we have only 1, and 2 on left. So this is the context window. So do you see he again?
Yes, sir.
So that is the fourth occurrence. It means that between
Sir,
it and
are
he,
we fixing our window size, context window size to 2?
right, the context window size is 2, right?
Right.
So that is the reason why between is and he, the co-occurrence is 4. Now, if I do between, say for example, lazy and he, what do you think? Lazy and he. What should I write here? Lazy and he. You
Sir,
can
window size, sir. Window size क्या है?
2, same 2.
And then 1.
Sir, 1. Sir, 1.
1, sir.
Lazy and he. Lazy and he.
This is
1.
just appearing
Yes,
single
sir,
time.
it's 1.
After
It's 1.
yes,
It's 1.
It has to be
sir,
1.
1.
How about he
Yeah,
and
sir.
he? How about he and he?
Sir, 0.
0, sir.
0.
0.
Right. How about he and not?
One.
One.
Two, sir. Two.
Yeah, two.
Two.
Two, sir. Two.
Two.
Two, sir.
Okay.
One.
That's
Two, sir, two.
Two, sir.
okay. Great, great. I think we are clear. So we actually fill this whole matrix. You can see here. We were right. Here we need 4. Here we need 0. 0, 4. We filled it 2. Yes, we filled it 2. And then 1. So there is 1. So lazy and he. Lazy and he. That's 1. So we have done it correctly. Right. Now see, I mean, this co-occurrence is actually telling you how friendly two words are with each other. How friendly two words are with each other. And if you
Sir?
use, yes,
Sir, maybe my question is very stupid, but when the word is same, the occurrence means the co-occurrence is 0. I mean, it's not making sense to me. But the word is same and the co-occurrence is 0. I mean, why?
I mean, when we say co-occurrence, we are considering two unique words.
Word.
Here, these are not two
Okay, sir.
unique words. So,
Oh,
co-occurrence of share with share is 0. Now, can you see in a ceremony share with share? I mean, yes, you can see if I am fighting with Arthur, riding on a
It's possible
lion,
in Pakistan.
on lion, having a sword in my hand. That's possible. Share with share, but generally,
Shut up.
generally, word does not appear with itself because we want to see how friendly two unique words are with each other. Right.
now I got the point, sir. Yeah,
Okay.
sorry.
Sir, if we keep our context window side to 0, then we can say it's 1. But it's not the case.
Okay. That's another way of looking at it. Very good, very good. So a co-occurrence matrix of size, again, it has got some disadvantage. The disadvantage is if you have got a lot of unique words, size of this matrix will become very high. So it may not be again a very good way of representing words with each other, right? So the obvious disadvantage is it is again kind of a sparse technique. I mean, a kind of where we need a lot of memory. Even if you remove stop words, if you have got n which is subset of v, uh, and inside n you have removed all stop word, then still computational difficulties will be there because you still need quite a big matrix which can represent this type of relationship, right? Again, another issue is there. I mean, you are referring to the window size, huh? Generally, words which are very close to each other, they may not be in immediate window. They may not be maybe 2 step away or 3 step away or 5 step away. They may be 1,000 steps away, but they still might be friends of each other. So the important thing is, I mean, yes, when we did not have other techniques, this co-occurrence matrix gave us a very good way of understanding words, just to figure out how frequently words are occurring together, rather than just focusing on one word. Now we were focusing on co-occurrence of the word. Okay, that was a good idea. But when these disadvantages were perceived, I mean, we need bigger memory. We again had a sort of sparse embedding. So we actually thought, I mean, then we went to the prediction based. I mean, here we were doing feature engineering ourselves. We were learning what should be the number I should give to a word, based on co-occurrence, based on its frequency, and without considering these two, just one hot encoded. I mean, these all things we were just trying to give some number to the word. But then we thought we are in deep learning. Why we are learning these numbers ourselves? Why we are counting words and then giving them appropriate numerical representation? We said why can't we give it to the neural network to learn itself? This word to wake, I think it came in 2007, 8, 9, not sure, or maybe 2009 or 10. In word to wake, they said you don't need to count words. You just give words to neural network. Neural network will learn weights by itself. We said rather than Irfan, Khalid, Nimra, Saif, you people will be using this technique because we have promised that end of the day
Yes, sir.
we will be providing, a word embedding for Urdu. So you need to
Yes, sir.
learn how to learn word embedding, right? So word to wake said you don't need to count numbers, their frequencies, maintain matrices. You do nothing. They said give them to neural network. Neural network will give them initially some random values and then see the accuracy. If accuracy is good, then those values might be ideal. But if the accuracy is not very good, then network will run its learning process. Maybe initially it might say that ball should be represented by zero point 0.5. But when it gave zero point 0.5 to ball, it saw that accuracy was maybe 0.19. And then
Sir,
it updated the representation of ball to maybe become zero point 0.6. And then it saw that accuracy is improving. It means that this feature, if I continue increasing and if accuracy is also increasing, it means that I'm in the right direction. So my representation for this word now should be some number which gives me increase in accuracy. So they said you don't need to give, any number to the word. Let network learn what are the most appropriate word for these, what are the appropriate numbers for these words. They came up with word to vector, which is actually combination of CBOW and skip gram. The CBOW is actually continuous bag of words, and skip gram model. Both of them actually work together. One is actually kind of replica to other, uh, and when both of them you combine together, you actually learn embedding for the words, which are very good representative, and then eventually they assist you in good classification. Right. So let's see how word embedding is learned. Irfan,
yes, sir. I have a question that how do we validate word embedding? I mean,
how we validate word embedding? We
yes.
actually validate word embedding by looking at the labels which we have already assigned. See here, if I am giving it 10 documents, right, and I say you will have to do training on these 10. 5 of them are belonging to sports and 5 of them are belonging to entertainment. You do some pre-processing, you remove is, am, are, these stop words, right? Now,
Uh,
what the embedding layer will do, the embedding layer will actually get first word, give it a random value, and maybe 2 3 hidden layer, and see the label. If the label for first document is sports, and if the label predicted by the network is entertainment, it means there is an error. Go back, update the value. If the value previously you gave zero point 0.5, now change it. If you update value and if you still incorrectly predict the label, but you see error is reducing, it means you are in the right direction. Then you can come back, update the weight. So they said rather than assigning values to words by counting frequency and all these things, they said why you're doing it. If it is deep learning and you say that you just give image and do not give histogram, ages, and all these things, then in text, why you are learning features by yourself? Why you are doing feature engineering when you are doing text processing? They said, come on, you've got word to vector. Word to vector, initially random values to each word. See if those random values are predicting correctly. These might be the ideal, representation for the word. But if not, then do the back propagation. So back propagation will ultimately be updating, values for your words, and eventually, uh, I mean, all the words which are close to each other, they will have values which will be very similar to each other, and those words which are very dissimilar to each other, they will have values which will be very different from each other. Right. So
But
this
sir,
yes, Irfan.
this word to wake and fast text, these are developed on the corpus of Wikipedia and Common Crawl, right? But how they were trained actually, that these words are the optimal words which they have learned. This is the only way to see for classification.
They were
I
trained.
mean,
They were trained like this. They were trained in this way. They were trained CBOW, CBOW, CBOW. They were trained like this. Just one hidden layer and
right,
output layer, obviously, uh, because we are learning word embedding. We are learning word embedding. So we say for X1, what should be the label, for X2, what should be the label, for X3, what should be the label, and so on. So the number of
sir.
inputs are equal to number of outputs, right?
Sir, I got the idea. It's a learning process, but how these are validated? I mean, it depends on model to model that we have trained this embedding, and when you applied on this, it performed well. Like this, we will compare like this
Mhm.
validation.
Right, right. The validation will be done by looking at how accurate that embedding is. See here, Irfan. See here. If you are getting this output from here,
Right,
this is nothing but text. This is nothing but text. But this text is in number form. For example, this is Apple. For Apple,
right,
they have given you some number. Now, what you will do, you will take these number and give these to neural network to do the classification. Now, when you're talking about
okay.
ABC corpus, this is kind of embedding layer. This is kind of
Mhm.
embedding layer. So we say that when you use these embeddings, if they give you accuracy which is not optimal, which is not very good accuracy, you actually come back, you tell the embedding layer that update your weights, because this embedding is not giving us good result. So they will not only update, hidden layer of the neural network which is used for classification, but they will
Right,
also update the weights of the embedding layer. So this is kind of embedding layer. We have given input. It is giving us embedding for each word. These are being used for classification. Accuracy is not very good. Come back, update weights for all the layers, including the embedding layer. Come back again. If accuracy is good, come accept it. If it is not good, update the weights. Not only update the weights of hidden layer for the actual classifier, but
mm,
also weights of your embedding layer.
embedding.
So they
But sir,
say rather than learning embedding by counting frequency and other things, they say learn embedding along with the classification. They say consider these words also weights of the network.
fine.
If you consider them as weights of network, in the process you are improving accuracy of the model, you also improve representation of these words. Right. So
I mean,
so
but
every
sir,
time,
still,
yes, go ahead.
see, they have trained fast text word embedding on Wikipedia articles, right? They say, but what they would have actually done, they would have classified that this representation is classifying good, that this belongs to a particular category. This is the only way to train a word embedding.
Uh, this
I
is not
mean, I'm
only, there
talking
are
about
many others. There are,
validation of
uh,
validation of the learned weight through this embedding layer
right.
through classification.
I mean,
I mean, like experiment we performed for BBC Urdu text, right? The accuracy was good before applying the fast text word embedding on a simple network. When network was learning weights itself using embedding layer, it was performing better than the learned weight from fast text. So that's why I came up with the idea that because we had a very formalized text, news text, and those embedding which is learned on Wikipedia text is informal text or maybe written by anyone can write on Wikipedia. That's why we need a word embedding which is trained on a very formal and organized documents.
right, right, right.
So it depends on application to application that
Right.
if
See here,
maybe
Ifan,
one embedding
Ifan,
performing good on one data and may not
right.
be on another.
In your case, do you know what you need to do? Because I understand your question. Your question is you have learned embedding, but how you would verify that these embeddings are good? You
Yeah,
will
generalize
verify.
that.
You will verify by applying it in some classification task, in some translation task, in some prediction task. For example,
Right.
when you will be learning word embedding for BBC Urdu, what you will do, you know that you have got 1 million document falling in 5 categories, huh? Maybe zero point 0.2 million for each of the category. You use 0.2 percent, I mean 20% data for validation, 80% data for training. When you train the network, right, and when you see the accuracy, you learn embedding from the embedding layer, you train the network, you see accuracy is good, it means that the embedding which we have learned through embedding layer is making some sense, right?
Right.
Now you say you are saying that because they have been learned, this embedding weights have been learned on huge text which is generalizable, you say that the language that BBC Urdu and Geo, all of them, the language that they are using is applicable to not only in this domain, in news domain, but it is also applicable in Twitter. It is also applicable in social media, in formal writing, in books. So you say that the words for which we have learned representation from BBC and Geo, it is generally usable. So what you will do, you will actually take output of embedding layer. You will take
Right.
output of embedding layer, save it, and you can
Mm.
publish it. Ask the public to use this pre-trained word embedding. So you will not only be using your word embedding for classifying all these news articles, but you will
Right.
also, from the first layer, you take the output, save it, and name it as Urdu word embedding. And people will
Right.
use your word embedding, which you have learned on quite huge amount of text. Now,
Right.
your text is telling you, ball, runs, these are friends, right? Because
Mm.
they are occurring together very frequently. And this embedding layer will learn this relationship. It will learn that Nawaz Sharif, Bilawal Zardari, Imran Khan, 18th Amendment, Dharna, Jalsa, these words are quite friendly to each other. They are occurring
Mm.
very frequently with each other. And
In
because they are
politics
occurring very
context.
frequently with each other, it means that their weights will also be accordingly adjusted. The words like
Mm.
ball, 18th Amendment, they are enemy of each other. They very infrequently appear each other. Now, in news, if their occurrence is low, generally their occurrence is low. You want to generalize it. You say that
Mm.
this thing is generalizable because the vocab that sports article writer have used is very much specific to sports, and the vocab that entertainment guys have written, that is very specific to entertainment. So you say that this relationship of words which I have learned on 1 million documents is actually generalizable, because generally people use ball, bat, runs, run out, uh, catch, drop, bold, These words they use very frequently with each other. Yes, it is
Right.
not that the frequency of ball with Imran Khan is zero. It is not that frequency of bat with Nawaz Sharif is zero. But you know, frequency of bat with ball is much higher than bat with Nawaz Sharif. So the words which are friends of each other, their weights will also be very close to each other. So you
Sir,
are
we can.
embedding, you can generalize it. Validation,
Yes, sir.
validation, you will apply on the task. You
Right.
will say that we have applied it on 1 million document and it is giving us 90% accuracy, which is a
Right,
good
sir.
indication that this is a good accuracy. Right.
Sir, for our project, I got a small experiment for Sir Safe from this idea. We have text for BBC Urdu, right? So apply the BBC text Urdu and learn words. And I am giving Sir Safe a data set of Geo News and see whether it's classifying it's good or not. This can set us, as a base case for us. Like if a embedding learned on a formalized document is actually performing good on formalized document.
Very
By
good.
this now we can do this.
Very good. I mean,
So in free BI,
these small experiments, these are very
आ
exciting
जाएं
and
फिर
they
ही आए
give
हो
you
जाएं
evidence. Right?
sir
You have something to contribute?
I mean, this will build our case strong. See?
Yeah, you're right. You're right. You're right.
yeah Irfan just share it on WhatsApp group and I will do accordingly inshallah.
Okay. Good. I think we got the idea. Huh? We got the idea.
Right.
Okay. Now, see, let's understand these two concepts: CBOW and skip gram. This it is continuous bag of words. Bag of words means you're not considering sequence. You're just considering all the words in bag, and they really are jumbled. They don't consider sequence. They just see if they are considering in one document or not. Right. And in bag of words, really we ignore sequence. They predict a probability of a word given its context. Context can be a single word or it can be a set of words. See here, this is just one example. This is just one example. If I say this is my corpus, hey, this is sample corpus using only one context word. Now we say if I give this input, this should be output. If I give this input, the output should be its context. I want to predict the next word, right? So I don't mean only next word, but I mean word in the context. So here, by the context, I mean just one word on left or right, right? So see here, if I say hey, the output should be this. If I say this, output should be hey, and if I say is, output should be this. Huh? Is its context is not only this, but its context is also sample, right? So we say for is, the context word is this as well as sample, right? For sample, the context word is and context word is corpus. For sample, you can see one window, context word is as well as corpus. For corpus, it should be sample and using. So you can see here for corpus, it is sample and it is using, right? Now, we can consider all of them, data points. You can say this is your training set. This is your training set. Now you are giving, say for example, one hot encoding to all these words. For example, for hey, this is your input. Your input is 1 0 0 0 0 0 0 0 0 and 0. Now, if this is your input, what should be your output? What should be your output? If input is 1 0 0 0 0 0 0 0 0 0, what should be output?
Hey.
Hey,
What should be output?
hey,
No, I mean, hey is your input. Hey
So
is
this
the
Output should be
this,
This.
yes.
this embedding is for hey. This one hot encoding is for hey. Now, if the input is hey, what should be output?
This, sir.
this
This output should be this. And what is one hot encoding of this? It is 0 1 0
1
0 0
0
0 0 0 0 0. It means for data point 4, what is data point 4? Data point 4 is
1, 2,
is.
3.
Data point 4 is, which is
is
0 0 1 and all other 0. Huh? data point 4, data point 4
Sir,
is,
is sample.
is the data point is 4.
Is
Yes.
it repeated 2 times, sir?
Age is repeated for 2 times, but what should be output when data point 4 is there? What should be output?
Sample.
Yes.
Sample.
Yes, the output should be sample. And for sample, encoding is 3 zeros, 1 in all of the
One.
zeros. You can see 3 zeros, 1 in all this. So sample, output should be sample.
Sample.
It means
Output.
that they say do nothing. Just have one input layer and have one output layer and do give these on input, and you are expecting this. That's it. This is your x, this is your y. Have only one hidden layer. In that one hidden layer, obviously you will have weight matrix here, which is v by n, where v is the number of words in your input and n is actually number of neurons in the hidden layer. It can be any, I mean, I've been telling you since the first day, how many neurons in hidden layer we don't know. We will learn with the experiments. So you will have one matrix W, which is V by N. V is number of words in input, N is number of neurons in hidden layer. And then we have got another weight matrix, which is N by V, where N is number of neurons in the input and V is actually number of neurons at the output layer. And output layer and input layer will have same number of neurons, because we want, we want, if this is input, if A is input, A has this embedding, the output is this. This has this embedding, and both of them have got same number of neuron. That is the reason why input and output have got same V number of neuron. Right. So you just develop this type of data, and what should be their actual numbers, you let the neural network learn it. So when you learn these weights, these are nothing but embedding for the dictionary that you are giving to the neural network. So they say that it is not only, you can see here one example. When context word is this, this is the encoding for this, encoding for this, it is 0 1 and all 0. So you can see this is encoding for this. Suppose this is a hidden layer, right? This is hidden activation, and then you will have weights at the output layer and activation at output layer. It will do some prediction. It will do some prediction. So if I apply softmax on this prediction, you know that for the context word this, it might be doing wrong prediction. When it does wrong prediction, we say update these weights. Update these weights. Right. Not only you can have one word at input, you can have multiple words at input. You can see here now, rather than sending only one word, I am sending multiple words at a time. You can do it. I mean, in practice, we do it, because when you're sending only one word with the context word, your learning process becomes very slow. So they say that you can even apply multiple context words. Right. So in that case, we have got C1, C2, and C3. When you are sending these three words, you are saying that tell us the prediction, and if their prediction is wrong, then you will say that update the weights. Right. Skipgram is nothing, just a replica or the mirror image of CBOW. In CBOW, we say that we will have one word and we would like to predict context of that word. So if I'm saying the word is sample, my target is to predict is and corpus. I want to predict two words, which are the context word of sample. Right. So that actually becomes something like this. You are giving input a one word, and this will give you the context word. So, end of the day, when you talk about word to vector actually does both things. It runs one pass to give multiple word to predict the, I mean, to give the context and get the original word and then change it to give the word and see the context word. These both embeddings, they are concatenated and they actually convey, a lot of information about what should be the true embedding for a word, which gives you better accuracy. Right. So this word to wake is actually based on CBOW and skipgram, and they are nothing, just one layer neural network. And data depends on you, what data you are giving. Whatever text you are giving, they will give you what are the most appropriate weights for them. And obviously you will verify, because generally when you are learning embedding, you actually learn embedding with a supplemented task, and that task might be classification, might be neural machine translation, it might be next word prediction, it might be question answering. So, usually when you are learning embedding on your own, you will have a supplemented task with that. It usually works as a first layer. So it's not only that you will be learning embedding, but at the same time, you are also doing the validation. Right. We have to.
Sir,
Yes, 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 yes.
in this word building, do we also remove stop words and the repetitive words, or we keep the whole text as it is and give it to a model to learn?
I mean, more often than not, we know that stop words are not good. It's quite obvious that stop words are not good for classification. They are actually.
But sir, embedding has to be generalized. So if there is a stop word, it will have a less impact on classification task. But
See,
when we
see.
develop an embedding, don't we
uh,
make it generalized that every word in a dictionary should have a specific number, a weight?
Irfan, if you are doing classification, then remove stop words, because you know that stop words are not contributing in classification. They
No,
are
no, sir.
not
I'm not
separate.
talking about classification.
But if you're
I'm
doing,
saying,
machine translation, neural machine translation, there for is we need hai in Urdu. So we have to maintain is. We have to keep is. We have to learn what is the number representation for is. So in those tasks,
right.
obviously you will not remove them. But for classification tasks, when you are absolutely clear that these are very bad separator, then stop word removal is usually a pre-processing step in deep learning.
It's sir, but embedding, we need to develop a trained embedding on a whole available dictionary of Urdu, right?
Uh,
So that
you're right.
yeah,
You're right. But Irfan,
then see, if someone is applying on a classification task, obviously he will be removing stop words. Then if he will be removing stop words from that corpus for classification task, then
very
it will
good.
not be using the weights from those embedding.
Hmm,
But if someone is applying the same embedding
hmm.
for a text sequence task or text generation task, then he might need to,
Wow, wow.
those weights,
That's
because
great.
that's why embedding has to be generalized for the
Right.
available all words in dictionary.
You are right. Absolutely right. Absolutely right. I mean, if you are using it for your own specific task, which is classification, remove stop word. But you are right.
Yeah.
If you want to generalize it, you say, no, my word embedding, uh, I will, I am expecting that people will use for machine translation. People will use
Right.
for, many other words, and they will be needing these words to translate. In order to make
Right.
it general embedding, you are right, we must not remove these words because we need their representation. And you are right, even in classification, when people will be using, they'll be removing stop words. And when they will be removing
Obviously,
stop word, they will not use our
these representation.
embedding for as AMR. You are very right. I mean, your concept is very much clear in that regard. I totally agree with you. Okay, then they came up with GitLab. Huh? GitLab, it has been, I think, developed by Stanford in 2014 or 13. I think 13 or maybe 14. But GitLab,
Yes.
they say they do not only rely on local states, they get global information. I mean, that is the reason they call it a global vector. They say,
Mm.
come on, what you guys are doing? Huh? You just see the context, huh? This one word and its window. Window size maybe 3, maybe 4, maybe 5, maybe 10. But bigger the window size, higher will be the memory requirement. Bigger the window size, this will increase. The corpus size will increase. Gilov actually came up with a very good idea. They say uh, you you shall know a word by the company it keeps. I mean, this is also true for human. And they said, why you have forgotten word co-occurrence? And they say local context information is okay, but you also need global information. So they said rather considering a window, you just consider a whole document, right? Uh, they said you still need co-occurrence matrix and use that co-occurrence matrix, but not the way you were using it in past. So the main idea behind GitLab is you can drive semantic relationship between words from the co-occurrence matrix, the one which we abandoned when we started neural network. But then GitLab said, no, 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 it is still useful. How? They say that given a corpus with V words, the co-occurrence matrix X will be V by V, like this one. The cat sat on mat. The cat sat on mat. Each cell Xij denotes how many times word I and J have occurred together. When I'm saying together, I mean in whole document. In whole document. So if I just open maybe one page of say for example maybe I say dawn.com. If we see this page, for example, inside this, if I take Germany word, then I want to see the co-occurrence of Germany with say for example COVID, with COVID. So Germany, and then you can search COVID on this page. You can see co-occurrence of Germany and COVID-1, co-occurrence of Germany and COVID, maybe you can see 2, and so on. Right. Now they say that forget about window, talk about whole document. Right. Now you just see how many times Germany is co-occurring with COVID. Bigger the frequency, higher are the chances that these two words are very related to each other. Then they say it is not only that you see their co-occurrence, but you also use a third word. You can call it a probe word. That probe word will give you more meaning that how strongly these two words are related to each other. They actually paired with probability. You can see here, I mean, their original paper, they have actually given this example. So I'm also using this example. They said, if you, this is the conditional probability, they said, what will be the probability of K given ice is there? The co-occurrence of ice and K, the co-occurrence of stream and K, right? They said now you can see relationship between ice and steam, by this ratio, but that ratio is through some other word. For example, if K is equal to solid, it means that probability of solid given ice is also appearing. Now, these two words are probably foreign to each other because ice and solid, they have some relationship. Ice is solid, right? Now you can see they have actually, I think on 1 billion tokens, they actually got all the information from, I believe, Wikipedia, and then they collected 1 billion tokens and in different documents, and they saw that the appearance of solid and ice together is 1.9 into 10 power 4, whereas occurrence of ice with gas is 6.6 into 10 power minus 5. So you can see this relationship is stronger. This value is somewhere around 0.00001, and this value is somewhere around 0.0000006, which is quite smaller than this value, right? So they say that, wow, ice and solid relationship is quite big, and that makes sense. Ice with gas, because ice is not gas, right? That's very small. Ice with water, oh wow, they have some relationship and they are appearing very frequently with each other. So that is 3 into 10 power minus 3. And ice with completely irrelevant word, which is fashion. It is only 1.7 into 10 power minus 5. So you can see they give you co-occurrence of two words, and then they see how much they are related with each other with the third probe word. Now the probability of K with stream, right? If K is solid, then it is this value. If it is gas, it is this value. If it is water, it is this value. If it is fashion, it is this value. You can see steam is completely irrelevant to fashion. So this number is quite, small, very small. And if you see that steam and water, they are bit related to each other. So you can see here their occurrence is having, some bigger number, at least when you compare it with this one. Now they say, if you want to see that what is the relationship between ice and steam, you can see this relationship by this ratio. Bigger the ratio, higher is the relationship. So they say that
Really?
if you want to figure out if ice is connected to steam, you see how ice is connected with solid and how steam is connected with solid. And you see that ratio. If both of them are very similar to each other, this ratio will be very close to 1. And if both of them are very dissimilar to each other, this ratio will be close to 0. So bigger the value of this ratio, higher is their similarity, and lower this ratio, closer that will be to 0. So they say that rather giving context window and these type of things, you just use this probability, and this value then can be used to actually generate the embedding of the word. So that was the general idea behind GitHub. And then they actually, you can see, is very similar to ice but irrelevant to steam. The value will be very bigger than 1, but end of the day when you see uh, if it is related or unrelated to either word, probability will be close to 1, right? So end of the day they say this ratio is giving you lot of meaning, and then you can use this ratio to actually do the embedding. I mean, they have later on used this probability in dot matrix for learning the actual vectors. You can refer to the original paper, but the whole idea was, rather than relying on any window size, you just concentrate on whole document. And then I mean, they actually wanted to learn vectors which can make lot of sense. They said that I think original GitHub paper should be there. I should open that paper, which will actually give you more understanding that how good vector they have learned. GitHub, Stanford paper, original paper, Stanford original paper, GitHub. I think it is this paper. If you see the embeddings that they have learned, this paper you must read. I have taken this example from here. You can see they're learning this probability, but when they learn, they actually learn these type of embedding. Is it here, or maybe I've seen it somewhere else? But queen versus queen king. You have seen that example, eh? You have seen queen and king examples. They have not given
Yes.
in their original paper. They have not given in their original paper, but I think I have seen it somewhere that that maybe Excel, no, maybe in this whole presentation. They say the embedding that we have learned can actually be making sense here. King minus man minus man, king minus man,
Equals
no, king minus man plus something. It will be equal to queen.
queen.
It will be
Yes.
equal to queen. King minus man plus maybe I say royal family, huh? Or
But
maybe
still, it will
uh,
work with this king minus man queen,
It will work, sir. King minus man equals queen. It will work.
queen.
because king has been learned in the context of
Yeah.
royalty.
King is already royal, sir. King is
But king
already royal.
minus man. अगर आप king minus man, there is something else which I'm missing. Uh, king minus man, king minus man.
Plus woman. Plus woman, sir.
Ah. Wait, I mean that's what I was thinking. If you take man out of king, there should
Obviously,
Yeah,
we have to some. Obviously, we have to something.
right, right.
sir. Sir, still
Some
see,
living things.
there
Yeah,
could be another relation. King minus man plus boy. It would be prince.
it will be
Yeah.
You're
Yeah,
right.
we
You're
can
right.
do
You're
that.
right. You're right. You're
Yeah,
right.
we can do that.
You're right. You're right. Now you know what?
And king minus man plus girl princess, right?
You're right. You're right. You're right. I mean, the idea is the embedding for king, the number that they have assigned to king, and the number that they have assigned to man, and the number that they have assigned to woman is actually satisfying this relationship.
Mm.
And it is only because they have learned these probabilities, they have learned this ratio, and the ratio has been learned from around 1 billion tokens. uh, and,
Wow.
and they have then trained it on the neural network, but end of the day the embedding that they have learned is actually so accurate that even this equation is satisfying. Even this equation
Sir,
is satisfying. And when they are plotting bad and good, good is here on the plot and bad is here. And when they are plotting, beautiful and ugly, the distance between beautiful and ugly is also same. So they are saying that in the language, the semantic that we wanted to capture, it has been captured by Gilov, and it has been captured only by understanding, the simple concept of probability, which actually says you need to learn this ratio. Do you want to see how ice is related to steam? You need a probe word. And that probe word can be solid, can be gas, can be water, can be fashion, in any other probe word. And if ice is very closely related to solid, and if steam is also very closely related to solid, both of these numbers should be high. When this number will be high, this should be very close to 1. But if say for example, ice is close to gas, but steam is also close to gas, then their similarity should still be high. But if say for example, I am comparing ice and fashion, right? Now here I keep fashion, here I keep ice. You know that fashion and solid will have a very low number, and steam fashion is here, fashion is here.
mm,
Fashion and solid, it will have very low number. Ice and solid, it will be very very big number. So they say that if it is related or unrelated to either words, then this number will be very close to 1, otherwise to 0. So this probability is actually kind of maintaining a relationship between words only if you have got a third word as a proof word. You need to learn how they converted this probability into actual embedding. They actually do some dot products and some symmetry rules, huh? They start from here, they actually start
mm.
from here, huh? Word I, word j, and probe word. So this is the formula I already told you. And then they said, because you want to learn basic arithmetic, you want to understand the difference or sum between the word. So you can replace wi and wj with wi minus wj, robot is still same. And then you can you know you can do a whole transpose mathematical, that's okay, right? You can replace a probability of ik. It means that you want two matrices. One matrix is for wi, other matrix for wk. These are actually two matrices, weights. These are two weights, and you want to apply some function on those, right? Same, you change p j k with wj and wk, because both of them are again matrices, right? So they do this simple math, apply log function, huh? There has to be some function, so they say log function, and then they do this dot product by applying some integration. End of the day, they say that you will have a beautiful formula like this, which when you apply on the words, you can learn embeddings which are very accurate. I mean, they are as accurate as satisfying this relationship in real world. So the
Sir,
whole, if on just one thing, so the whole concept of GILOV is global vector, not local vector. We were focusing locally on the window size. These guys said global, increase your vision. You just see that frames of the words may not always be in close proximity. They might be, located far away from each other, but they might still be very good friends to each other. So they said focus globally rather than focusing in a window side. Irfan?
sir, the idea is brilliant, but sir, can we give it a one more confidence vote by just they have seen they have counted the co-occurrences of these words, and on the basis of that they have calculated the probabilities. But can we do this like this? Count these co-occurrences and number of times it has appeared in the whole window or the whole globe. It will even strengthen this concept, because I haven't read the paper. What idea I have got, they
I mean,
might would have.
you are then again going back to TF-IDF, eh?
Yeah.
No, along with this approach, if we incorporate that as well, that it will give a more confidence to embedding that yes, these are occurring in a global window, but how many of times in number of documents in different contexts.
I mean, yes, we can do a lot of modification to that. We can think over it. I mean, uh, that is my, basic, target. It's not only that we should be applying what Stanford has done. Maybe if we understand mathematics of these, we might introduce some, modification which can be bringing some revolution. I mean, you're right. You're right. You should think in
I
this
mean,
direction.
I haven't read it, but I don't know whether they are taking context into account.
No, no, they are using just this one. They are
See,
saying
for
that.
sports, sir, just a small example. For a sports hockey, ice and solid would be there for a sports hockey game. But in a different context, in let's say suppose in drinks, ice and solid is ice and solid and plus water. Will be context will be different.
Hmm.
So,
You're right. You're right.
if they take context into account, I mean it will be more even.
Irfan, you are now bringing the discussion that Gillard could not address. I mean, they say that.
Sir, I haven't read that paper.
Yeah, they said that well, ice is occurring in a sports document where they are talking about ice hockey. There, the meaning of ice is different than the ice which is discussed probably in a home environment. Give me a piece of ice, give me some ice. Their ice is different. Say for example, if I say I'm sitting on the bank of river, is different than I'm saying I'm going to the bank. So they said
Yes.
that when you say bank of river, it their bank should have different embedding, and the I'm going to bank here bank should have different embedding, but Gillard failed to do it. Gillard just said,
I'm not claiming it
yeah,
because
Gillard,
I haven't read it whether they are
yeah,
taking
yeah. I mean, Gillard
context
failed.
into account.
Gillard failed to capture this context. That is the reason why we saw attention. I mean, the point that you are now raising is
Right,
actually part
right.
of attention. This is exactly what attention says. This is exactly what is our next topic. Our next topic is attention. Our next topic is
Right.
actually attention and transformer. You will see that in attention, we will be discussing this concept. Uh, I think somewhere I have written this example. I have written this bank example. I should have this example. I should. No. Yes, here you can see it. If you drive down the road and follow the river bank, you should find Bank of America. Huh? Now Gillard says give bank and maybe river, if both of them are occurring together, give them same maybe close
Right.
numbers.
Numbers.
But it does not say what should be the embedding for bank when it appears with river or when it appears with Bank of America. So they say that word is same. My God, but its meaning is different. Here it is Bank of America. Here it is River Bank. So
Right.
Gillard gave one embedding to the bank without considering whole context. It actually considered word co-occurrence. Attention said, no, you can't do this. If you do this, then this type of context you will miss. River Bank and Bank of America. So they said to each word, you should not be giving only one embedding. You should not be giving only one vector. The vector of the word depends on where it is appearing. If it is appearing with river, here is its vector. And if it is appearing with the Bank of America, here is its vector. Right. So this is exactly what attention does. So when we will be covering attention, you will see that how these two words, bank and bank, will be given different embedding. Right. But we at least understand what is the problem with Gillard. Do you people want to continue?
It's up to you. We can't even say we'll miss our point.
That's the problem in online classes.
We can continue in next class, and we can have next class tomorrow or day after tomorrow. You can even place any time.
Tomorrow we will have those meetings with our NTNU friends.
Okay.
Uh,
Okay.
and I also need to progress on the paper that tomorrow we'll be discussing with them. So morning time I've already spared for that. We can continue.
Monday or Tuesday.
We can continue again next week because middle of the week I might be in travel. So if you see for next, I have sent you the link. So for
Yes,
5 for 411, 411, uh 4 11 18
16, 25.
25. We'll have 4 more weeks to cover remaining contents. And by the remaining contents I mean machine translation, what an idea, attention, transformer, BERT and GPT. So hopefully 1 week, one concept, and then we should be finishing the course contents. Last 4 weeks, but I must say this is where we wanted to reach. I mean, whatever we have done for past 9 or 10 weeks, the reason was we wanted to understand attention, transformer, BERT, and GPT-2. So these are 4 topics, and we still have got 4 weeks. God, Allah Ta'ala, created whole world because he wanted to bring Muhammad Sallallahu Alaihi Wasallam. They say ना कि ये दुनिया बनी है तुम्हारे लिए. So he created Adam, he created, you know, David and all other prophets. The reason was he wanted to create Muhammad Sallallahu Alaihi Wasallam.
Yes,
I was teaching you RNN, LSTM, all these things because I wanted to teach you attention, transformer, bird, and
Art,
GPT.
GPT.
So these 4 weeks must be very exciting. And honestly speaking, I'm happy
sir. We
that
have 5 weeks.
uh, 1 week we will be having your presentations.
Project
Obviously, you will be
presentation.
doing
Okay,
a lot of work, so I want to give you time also. We will have 4 weeks, I believe, not 5 weeks. We will have 4 weeks. We will have four
so
weeks.
as per calendar, we have 9 days from January.
Uh, no, that we have changed because now we are
Yeah,
not doing second mid. So,
but for MS, we don't have a mid,
uh,
second mid.
but we have to
One mid and
conclude teaching by December 24. But we will see. I mean, we might
okay.
conclude by December 24, or we might continue for till Jan 1st or 2. I mean, because it's online, it's flexible. So we can finish by 24, which is IBA's instruction. IBA says conclude teaching by 24, but we can continue for one more week if required. Because I understand that all these contents that we still have to cover, they probably will not be covered in 4 weeks. We might need 5 weeks, so we can do 5 weeks, no problem. But it's our commitment. I mean, it's a kind of agenda we have already said. We will cover attention transformer, uh, BERT, and then GPT 2 and 3. Right.
2 and 3.
So these 4 or 5 topics are remaining, and we still have got 4 or 5 weeks. And the good thing is, you people won't be around. The good thing is, we'll be doing it online. So whatever we talk, whatever we deliver, it will be recorded. So for rest of the time, we can refer back whatever we have done. And to be very honest with you, I enjoy more online teaching than face to face. Okay, Seth,
Same here.
Seth,
Yes, sir.
you want to say something?
No, sir.
Okay, okay,
We are also enjoying online, sir.
So the
okay.
CMS issue.
Oh, CMS issue. Yes, yes, yes.
Yes, sir.
Because we have Seth with us, so he can guide. Here's the key. You just
So,
log in.
I
You
mean,
just search.
no, sir. I can log in, but I cannot see the deep learning course. Earlier I can see, but now I cannot. I
Can
don't know
you
why.
can you search this one with 2px?
Yeah, I try to add that code, but it's saying that I cannot add. I mean, you need to add me.
From here, I can see participant,
Yeah.
enroll user, enroll user.
Yes.
The
Sir,
39 participants, sir.
yeah, I mean, it was a mistake. Actually, I shared deep learning key with my data science class. And on the
But you
very
haven't shared data science key with us.
so there are later, I mean, next class, when I realized that why they are registering deep learning, then they told me that because you gave us this key, so I gave them correct key, so they registered in data science. Too many users, uh, assign search, enroll user, enroll user, enroll user. How to enroll?
Sir, write his CMS ID.
Uh,
223-19.
double two,
3.
223-19
double two three
dash
dash
Here,
19.
here it
19.
is.
Yeah, that's the name.
First one.
Mohammed
First
Noor
one.
Lamin Pakedi.
This one?
Yes,
Yeah.
sir. Actually, I'm having my father's name at the beginning. Then I have my name. It's normally in Sri Lanka we go like that.
Okay.
But in
Okay.
Pakistan it's
Moment.
different.
Okay. Okay. I say enroll him. So you are enrolled, eh?
So
Yeah.
regarding the assignment, so have you
I will extend
extended?
the date here, now.
Have you? What do you
Yes.
say?
So have you extended the date or
No.
it's
Sir,
over
Why would I extend it? Let me check how many of them have upload. By the way, I have uploaded today's lecture, so you can read this and this. This will cover next week, eh? So
I
BBC.
mean, I'm not be able to access, so I didn't upload the
Sir,
assignment.
sir,
Uh-huh.
I shared the assignment, via Colab. I couldn't get it whether we are
Upload
supposed to
here
submit on.
because I won't be able to check there. Upload it here.
Huh?
Upload
But
it here.
Sir,
Only
all the
3.
assignments we have shared with you on Colab, sir.
we used to share with Colab.
And I have
Uh,
very
yeah.
blindly forwarded everything to deep learning folder. Deep learning fall 2020. All the assignments are here. Some
So, sir, you may create this assignment on LMS, then we
those
will
are
upload
already
there as
created.
well.
Those are already
Sir,
created.
this is for assignment 5 only.
Okay. But I see only 3 submission. Why? Abdul
Sir, we
Ghaffar.
have shared it on you with Colab.
Sir, we have shared via Colab.
Only 3.
Sir,
All the
I have
assignments
shared via
for us.
Colab. That's what I'm saying.
Send here.
Yes,
Send
the date
here.
and we will submit it again here on LMS.
Send
So
here.
I think you need to extend the date then.
Yes,
Yes,
sir.
sir.
Please extend the date so that we
Let
can
me
submit here as well.
okay, I can extend the date. Edit.
Uh-huh.
I can extend till tomorrow.
Sir, till
Yes.
Sunday.
Till Sunday. Till Sunday. Okay. November 28. 28, right?
No, sir.
29, sir. November 29, Sunday.
November 29 is Sunday. Okay.
Yes, sir.
Okay. Please do it by this time. Right. And do not email me.
We will submit it on LMS.
Submit on LMS. Otherwise, you will be increasing my role. Mid exam, I've already assessed. I have also given, grades to.
Sir, please let us show.
No, I have written those grades in Excel. I will show you individually. I should not show you here because people will not
Sir, share
be.
on WhatsApp group, sir. We will also see the marks
I
individually.
should not because the
No.
result is confidential.
Sir.
Result is, three idiots. They say if you taste them and if somebody have got AIDS, will you be displaying it on the wall that this guy has got AIDS? You
तो
can't.
सर एक और एग्जांपल था ना उसमें दोस्त फेल हो जाए तो दुख होता है दोस्त आपसे ज्यादा नंबर ले जाए तो और ज्यादा दुख होता है
सही बात है. That's true. That's true. Okay, guys, thank you very much. I will be keeping this recording on LMS. You can watch it later on. We will meet again on Friday.
इंशाल्लाह
Again, same time. I've already shared with you the link as well as the
Calendar.
ID and password, so you can log in again.
Sir?
On Friday. Yes, Nimra?
Sir, is it possible for us to change the day?
I can. I have no issue, but I know that
Change the
others might have
timings, sir.
issue.
Change the timings.
I mean, time is same.
No,
Time
sir.
is same as timetable.
Sir, same temple, then day doesn't matter.
Why you want change?
Sir, because now we are not coming to IBA and we are at home, and Friday is the day when, there is a lot of disturbance at home. So just that's why I'm asking. Otherwise, it's okay.
I can do it in morning time any day. It will be even better for me. But I don't know others.
Sir,
It might be
sir,
busy.
I have my own classes in morning time.
Better don't touch it. I mean, that is the reason why in IBA we made decision that will be following the same timetable. Because if we
Sir,
change,
that's fine. Sir, otherwise, that's fine. There is no any genuine issue. That's fine.
Okay. Thank you, Nimra. See you all next week. Bye bye.
Thank you, sir. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.